Welcome and thank you for joining Direct Electron's webinar on how to take control of 4D STEM that features our mission control and dimension software. We're glad you could attend, and we are very excited to tell you about our new products for 4D STEM here. In this webinar, you'll have the presenters will be myself. My name is Bob Monteverde. I'm the Director of Sales here at Direct Electron. But a majority of the webinar will come from our technical experts, Dr. Barnaby Levin, who is our application specialist for material sciences, and our in-house expert on 4D STEM. Will tell you more about how people are using our cameras for 4D STEM. And then Dr. Benjamin Bomis, who is our Director of Research and Development, will tell you about our new mission control product. What we'll go over in this webinar, what you'll learn are information about the cameras and products that Direct Electron has for 4D STEM. Then Barnaby will tell you about how the information-rich data that's provided by 4D STEM can enhance and benefit the research that you're doing. Then we'll follow up. Ben Bomis will tell you about some of the challenges that we have seen our users experience with 4D STEM and what are the areas that we needed to bring improvements to our product to make 4D STEM more accessible. So then we'll tell you about how our new mission control and dimension software provides real-time feedback and why this is important. And we'll then tell you about the future of 4D STEM and how it makes 4D STEM unlimited with new scan patterns, new sampling, and distortion corrections. So here at Direct Electron, we have been building advanced cameras for TEM for over a decade. And all of our cameras are direct detectors, meaning that they do not have a scintillator. They are directly detecting the electrons, which provides the highest resolution and the highest sensitivity. Direct Electron was the pioneer in this. We introduced the first commercial direct detector, the DE12, in 2010. And initially, our customers were using our cameras for primarily cryo-EM. But shortly after the introduction of our cameras, our users branched out. We started exploring applications in the material science spaces, including high-resolution materials, in situ TEM, as well as 4D STEM. In fact, we've been working with 4D STEM since 2016, initially with our DE12 camera. Initial publications came out about that time for using our cameras for 4D STEM. Then following that, with the introduction of our DE16, we had additional customers using our cameras, our DE16 for 4D STEM. And then a couple of years ago, we introduced our purpose-built camera for 4D STEM, the Celeritas and Celeritas XS. And we've had numerous users publishing very impressive papers, impactful papers on 4D STEM with our Celeritas product. Now, we've always been developing software along with our cameras, but what we realized with 4D STEM, there were new features and new capabilities that we needed to enhance with our software. And so we introduced Mission Control earlier this year, along with our Dimension software module that directly address the application needs for researchers in 4D STEM. So at this point, I would like to turn our presentation over to Dr. Barnaby Levin, who will tell you more about what 4D STEM is, how it's used, and how our cameras can help you. Thank you, Barnaby.
Thank you for the introduction, Bob. So first, I'm just going to give a quick overview of what 4D STEM is. I think most of the people who've joined the webinar probably have some idea already, but I'd like to make sure everybody's on the same page. So what you're seeing here are two diagrams, one showing the setup for conventional STEM, and the other showing the setup for 4D STEM. So as, again, most of you in the webinar will already know, in conventional STEM, you have a focus probe which you raster across the specimen, and you can use different detectors to sample a part of the transmitted or scattered beam. So a bright field detector, an annular bright field detector, an ADF detector. And these all give you one signal at each point in your scan, giving you a 2D image. The difference with 4D STEM is that instead of just recording one signal at each point in your scan, you use a camera, typically a direct detection camera, to record the entire diffraction pattern at every point on the scan. So you get a series of 2D images at every point in a 2D scan, and that gives you a 4-dimensional data set. And because you're recording the entire diffraction pattern instead of just one piece of information at each probe position, you have a data set that's much more information rich than a conventional 2D STEM data set, which lets you do more different types of analysis. So Bob mentioned that our sort of most powerful camera for 4D STEM out of the different cameras in our portfolio is our Celeritas XS camera. This is a monolithic 1K by 1K sensor that can read out at different speeds depending on how much of the detector you're using. So at full frame, it reads out at 1960 frames a second, and you can window down to run the detector at up to 87,000 frames a second, which is equivalent to a dwell time of about 11.6 microseconds. So this is a camera where if you want to, you can do 4D STEM basically as fast as you would be doing 2D STEM. And the different readout areas are designed to enable different techniques, particularly 4D STEM. So one of the ways that you can analyze 4D STEM data is to look at shifts in the position of the electron beam at different points in the scan. That's called center of mass imaging. And among the different things that influence the position of the beam are electric and magnetic fields. So one of the things 4D STEM can enable you to do is electric and magnetic field mapping. This image here is an atomic resolution image of strontium titanate, but we've processed it using a technique called center of mass, which lets you map shifts in position. And you can see donut shapes around the atomic columns in the specimen. And those shapes occur due to the electric fields around the atomic columns. And with Celeritas XS, we can acquire this data very rapidly. So this is a 512 by 512 probe position scan acquired in about 3 seconds. Another technique that's very popular is called tychography. So essentially, this is a way of applying computational methods to 4D STEM data to extract high-resolution images of your specimen at a lower dose than you can achieve with conventional ADF or bright field imaging, sometimes a significantly lower dose. So this is quite popular with people looking at beam-sensitive specimens or people who want extra high resolution information from their specimen. And this image on the right here, this is an image of tungsten disulfide acquired by the Voiles group at the University of Wisconsin-Madison. This is actually a 2000 by 2000 probe position scan. And again, to give you an idea of how quickly we can acquire this data on Celeritas XS, that 2K by 2K scan took about 48 seconds. Which for 4D STEM is very rapid. Another different type of analysis that you can do with your 4D STEM data is to look at crystallographic structure in the specimen. So you can look at crystallographic orientations, crystal grain structure, strain, and things like that. So another area of research that the Voiles group has been interested in are beam-sensitive molecular glasses. And what you're seeing on the left here are orientation maps of molecular glasses that were synthesized at different temperatures. All of this data acquired using a beam dose of less than 120 electrons per angstrom squared. And the color in these maps basically shows the orientation of the molecules in the glass. So you can see different synthesis temperatures lead to different degrees of order. And finally, we have in situ 4D STEM. So any type of 4D STEM analysis you can do, you can make it in situ by doing it repeatedly with time. So what you're looking at here is an in situ 4D STEM data set of a metallic glass material that's being heated in a heating holder to the point that it crystallizes. So in this 5D data set, you can see an in situ image series. Then because this image series was recorded in 4D STEM at each point in the image, you can also look at the crystal structure at that point. So you can see spatial variations in crystal structure with time and how the specimen crystallizes differently at different times. So an incredibly powerful type of data set that you can't acquire in traditional 2D STEM. So I've given kind of a brief overview of 4D STEM and some of the different types of information you can get from it. And now I'm going to hand you over to Benjamin Barnes, who's going to talk about the challenges that we've been tackling when it comes to 4D STEM software.
Yeah, thank you, Barnaby. So 4D STEM is incredibly powerful, as Barnaby has talked about. However, it works a little differently than conventional STEM, as he mentioned in the first slide. Conventional STEM has been used for a very long time. It's quite convenient and easy to use, primarily because you immediately see the specimen as you are imaging. So you get a live view of the specimen, as you can see here, as you are acquiring images. One of the big problems with 4D STEM is what you see on the camera is the scattering of the electrons at each probe position. So you see what may be something like a Fourier transform of the parts of the image that you're scanning. And unfortunately, none of us, I think, have the vision to be able to look at this and understand what is going on with your specimen. Is the specimen in focus? Is it a region of interest that you're really interested in? Is the feature that you are looking for actually there, etc.? So this makes these experiments very challenging because essentially you're flying blind. In addition to that, even after the experiment, what you're left with typically is an extremely large data set. As Barnaby showed the example of 5D STEM, that data set was about 1 terabyte in size. A sort of typical data set from a 4D STEM experiment would be a couple of 100 gigabytes in size. So these are not data sets that you can easily just open in a standard image viewer and view. It really requires some processing. So not only are you flying blind during the experiment, it generally takes you a little bit of time just to transfer the data or load the data to be able to see what you're looking at. So there's quite a delay in terms of acquiring the data and then actually seeing the specimen, which is what you're really interested in. So as Bob talked about, we implemented this new software called Mission Control and this dimension module for Mission Control. Mission Control is our software for controlling our cameras and acquiring data. This is a significant rewrite of our software compared to previous versions. There's a lot more features in the software, a lot higher ease of use. But then we've added this dimension module, which is really geared towards acquiring 4D STEM data and making 4D STEM easy. So on the left side, you see a list of 4 tasks. The first task in a 4D STEM experiment is setting up the experiment. So the left panel shows parameters that you can adjust for the camera. These parameters, if you see, there's one box that says preset. It says custom right now, but you can have lists of preset parameters so that you can very quickly load sets of parameters. And people like Barnaby at our company can also help you set up your own custom presets so that they're quick and easy to load and you don't have to adjust individual settings at any time. During setup, though, you would essentially set the camera length of your microscope. You center the beam on the camera. You're essentially seeing a live view from the camera. So this is not for looking at your specimen. It's really for setting up the experiment. And then using the last image acquired in setup of what the beam looks like on the camera, you go to step 2, which is defining virtual detectors. You can define up to 4 different types of detectors or 4 different detectors on our camera. Right now, I'm only showing 2 virtual detectors here, one on the left, one on the right. You can enable up to 2 more, in which case you would have 4 virtual detectors. Defining virtual detectors is simply a process of defining a mask over the image, and that mask will tell the software which pixels of the camera to use for various calculations. And you can see right here, we're using sort of a draggable interface to define this. We also have the capability of defining these masks parametrically, so you can just type in the numbers, the radius of the circle, for instance. There's also other shapes like rectangles and things that you can implement in the software as well. But for 4D STEM, typically circles and ellipses are used. And then finally, for each of the virtual detectors, you have a drop-down for choosing the type of calculation that you'll do. This is what's really powerful about this, is that instead of just always using a sum, which is sort of analogous to a conventional STEM detector, where you're just summing all of the signal within some ring, for instance. You can also define the calculation as a difference. So you can define two different masks in the same virtual detector and then calculate the difference between them. So you have one positive mask and one negative mask. And then you can also calculate the centroid, or the center of mass of this, which gives you the capability of measuring electric fields, for instance, as Barnaby talked about. Or with the objective lens off, you could do something like Lorentz microscopy and look at magnetic fields as well. There's also the measurement of standard deviation, and the standard deviation is a nice measurement for approximating the crystallinity of the specimen. If you have bright diffraction spots, you'll end up with a higher standard deviation than if you have sort of an amorphous scattering over the region of your virtual detector. The next step is to do a preview. This is using your conventional STEM cameras like the HADF detector to search around. So basically, in many cases, the HADF detector is integrated with our software, so that you can control it directly from our software and use the same scan sizes and everything in our software as you would for 4D STEM experiments. Finally, step 4 is to actually acquire the 4D STEM data. And this is as easy now as just clicking start on this panel. You see here you've got a selection of 4 different windows that you can display at any given time during the experiment. Right now I'm displaying the scattering detected by the camera. So what the camera sees is in the top left. I have 2 different virtual images that are being generated on the top right and the bottom left. I have the standard ADF detector, the HADF detector, on the bottom right. And you can see during that acquisition, you saw a live view from the camera, and you also saw the virtual detectors based on the 4D STEM data generating the image of the specimen live as you are acquiring the data. So it's happening in real time, as well as the conventional detector showing live. So you really are getting live real-time views of the specimen during your experiment. You're not just flying blind as you have been in 4D STEM in the past. One of the important things about this is that that allows you to not only view the specimen, but you can do more complicated things like the center of mass imaging to visualize the electric field. So in this case, you can see that we have generated live in real time this electric field imaging around the atomic columns of strontium titanate. And when you combine our software with our ultra-fast Celeritas XS camera, you can do this really fast, as Barnaby talked about. And so I'll show you a live real-time view of what imaging with Celeritas XS looks like here on this slide. So this is a Celeritas XS experiment. We are acquiring a 256 by 256 scan of strontium titanate with 38 microsecond dwell time. And you can see that we're doing this repeatedly. We're scanning the same specimen area over and over again. I'll play this one more time. And you can see an image from the camera in the upper left. And then you can see 3 different virtual images generated, including the center of mass image in the bottom right that we just showed a little bit ago. So all of this is happening in real time. You really get a full view of your specimen as you're doing the experiment. And going really fast has a lot of benefits. Not only does that give you fast real-time feedback so that there's no specimen drift and so that you can really have an experiment that's quite responsive, but it also allows you to capture a very large field of view. So just to show a comparison, With the Celeritas XS camera operating at its highest frame rate at 11.6 microsecond dwell time, you could acquire this 512 by 512 region of the specimen in just 3.04 seconds. So you're able to get a fast image and potentially in situ imaging as well by doing a 4D-STEM movie, a 5D data set. With Celeritas XS, you can do this with only 3 seconds over a relatively large field of view. If you have another detector that's operating at about a kilohertz, which many of the detectors on the market operate at about that speed, in that same amount of time, you'd only be able to capture a couple of atomic columns. And I would argue that this is not particularly helpful. Really, to be able to do very powerful experiments, very responsive, large fields of view, you need a very, very fast camera. And so that's what we have with the Celeritas XS 4D STEM camera. And pairing it with our new mission control and dimension software means that you get real-time feedback and these experiments become very easy. Finally, the data from the camera is also stored to disk. We are storing the data typically in HDF5 format. There's a couple of different file formats that you can choose. All of them are industry standard open formats. And these formats can be loaded directly into third-party software for processing like LibreTIM or Pi4D-STEM, so that you still have your data stored on disk and can do additional post-processing as you choose. So you get the benefit of real-time feedback of being able to see your specimen as you are acquiring the data, but you don't sacrifice the ability to do post-processing as well. You really get the best of both worlds. So with our new software, we really think that finally 4D STEM is easy. You see, there's just these 4 steps: setup, defining virtual detectors. You can preview the image in a conventional STEM detector, and then you click go when you are acquiring your 4D STEM data with real-time feedback, seeing the specimen. You can respond as you see changes in the microscope alignment, or make sure that everything's in focus. You can move around to different areas of the specimen, make sure you're capturing the right thing, etc. 4D STEM really is easy because now it's responsive, it's immediate, it's real time. You see feedback from the experiment. But what if you want more control? So there's been a number of papers published showing different scan strategies as a potential mechanism for reducing radiation damage, or maybe improving time resolution by getting rid of some of the overhead from flyback time, things like that. And so you may be interested in some of these things. As an example, you can acquire a conventional raster scan that looks something like this. This is what all STEM detectors or STEM scan generators are acquiring right now. It's simply going left to right, top to bottom. You have some flyback time on the left side, so every time it moves from one row to the next, there's some delay before it starts the next row, and you're just scanning in this method. But there's other strategies in the literature that people are starting to try and play with using their own custom scan generators typically, such as a serpentine pattern, where instead of having flyback time, you get rid of that by doing a snake back and forth. You go right to left and left to right, alternating, so that the beam is never jumping from one side of the image to another. And this is a potential way of improving the time resolution of your experiments. You could also imagine other sorts of scan patterns. In the literature, there's a spiral pattern that has been tried as well, where you start from the middle and you spiral outward during the scan. There's also fractal patterns like the Hilbert scan, which basically scans local areas of the specimen. So you can see this sort of works in quadrants in a way. And this is another potential strategy for doing your scan. And then you could imagine a distributed or leapfrog scan where you spread out the beam and you skip areas and then fill them in. This has been proposed as a potential way of reducing radiation damage of the specimen by giving local areas of the specimen time to relax essentially after they have seen the beam. And finally, you may say, well, I have my own idea for a scan. I want to do something completely different. And so I want to design my own scan patterns completely arbitrary. And so you might design a smiley face scan pattern like this. I have no idea why this would be scientifically useful, but it was fun to draw nonetheless. So you have all of these potential scan patterns that have been proposed or that you might imagine. And really one of the big problems here is that if you look at your current scan control software, you'll probably see something like this, which is a very limited set of features. You can select the size of the scan, you can select the dwell time, and maybe you can select the rotation angle. And if you click settings, you can probably define the flyback time. Besides that, there's really no other options in scan control. It's really limited. It's really built for scan controllers that will only do raster scans, and they're sort of locked into that type of scan pattern. What we've built is our DE free scan generator, and coupled with our software, you can see now you have a drop-down box when you're defining the scan area called scan type. This scan type drop-down box lists a large number of different scans that are built into the scan generator already, including all of the scans that I showed you already, plus some versions that say interlaced or interwoven. These are ones where you skip rows and then go back and fill in rows, so you're, again, potentially reducing radiation damage by spreading out the beam a little bit. So you have all of these different scan patterns that you can simply enable by selecting it from a drop-down list, and then you're ready to go. But then the last scan pattern is called XY file. And the XY file is a way of loading your own custom scan pattern based on a text file that is simply a comma-separated file of scan coordinates. So you tell it what the scan width and height is, what the total number of points are, and the total number of points does not have to be the same number as all of the scan points. You can have less points, in which case you would be subsampling, or more points, in which case you would be oversampling. But you tell it how many scan points there are, and then you create a list, comma-separated list of all the scan coordinates. It will load this in the scan generator and then use it for the scan. It makes arbitrary scan patterns possible, and this is now completely unlimited scanning. You have a not just locked into raster scanning only, but you have a large list of potential scan patterns that you can use, plus the ability to define your own scan patterns with really no limit to what those look like. So to show you what this looks like as an example, this is a Moore scan pattern, another fractal-based scan pattern. And you can see once you've selected this on the drop-down list, you simply scan with the scan pattern. You get live real-time feedback during it. And I'm showing an FFT of this image live as it is being acquired. You can see the vertical and horizontal line across the FFT from the missing information in here, and then when it completes, those disappear, and you see the spacing of the calibration grid, which is my favorite specimen. In addition to different scan patterns, though, you may wonder about subsampling. There's also a number of papers about compressive sensing and subsampling as strategies to reduce radiation damage or improve time resolution, so you may be interested in those options as well. We also have built into our software the capability of doing unlimited subsampling. So right below the scan type, there is a subsampling section where you can select a subsampling factor. So in this case, if I'm subsampling by a factor of 2, it means that about 50% of my scan points are being sampled. And I can sample that in either a random way, in which I'm randomly choosing 50% of the scan points, or I can choose it as regular subsampling, in which case I am skipping every other scan point. And so you get sort of a regular skipping across your image. And again, this also happens live. So once you select subsampling, now when you click start, you are now collecting subsample data immediately. This is a random 50% subsampling. I'll play this one more time. And you can see that, again, it's quite easy. It's a single box for selecting the subsampling factor. You tell it if it's random or regular, you click go, and you're ready to go. So it's a way of adding subsampling to any experiment or any scan pattern, including the XY files that you load. I'll mention that if you don't, if you want even more control over subsampling and you want to specify your own specific subsampling, you can do that by defining it in your own XY file, in which case you would ignore the subsampling box. This subsampling box is really just a way to make this an easy process. So there is a problem, though, when you add all of this this control over the scan pattern. So we've given an unlimited number of scan patterns now, an unlimited number of options for subsampling. So we've really taken the limits off of STEM and 4D STEM, and that's incredible. But Once you do this, if you're operating fast enough with a fast enough dwell time, so if you're either doing conventional 2D STEM, as the examples that I'm showing you here are, or if you're going very fast with a Celeritas XS camera, for instance, with about 11 microseconds dwell time, you end up seeing some artifacts in the images with different scan patterns. And this is because of the behavior of the electromagnetic scan coils in the microscope. This is simply based on the physics of how scan coils work. And in the same way that the physics of how electrons go through electromagnetic lenses give you things like spherical aberration and chromatic aberration, you also have different sorts of distortions and artifacts introduced by the electromagnetic coils of the scan system of the microscope. In this case, I'm showing an example of a serpentine pattern, and if you look at the left-hand image, you see sort of a doubling of the calibration grid, where you sort of see this left and right offset, and zooming in, you can see that essentially you've got a shift on every other row. So the rows that were required left to right are shifted relative to the rows that are going right to left. So you have this sort of strange shift, and it makes these very difficult to use. You may not realize it, but these distortions are always present in the microscope. So flyback time reduces the artifacts that you see, but you can see that there are still distortions if you simply use your current scan generator and you change the dwell time. So in this case, I'm using a 3 microsecond or 8 microsecond dwell time with a conventional STEM image. And you can see a horizontal shift, and this horizontal shift is due to the distortions in the electromagnetic coils. In the past, these distortions, in particular these ones like the serpentine pattern for people trying different sorts of scan patterns, have been addressed by moving pixels around. So you apply post-processing and you essentially interpolate the value of each pixel and try to shift pixel values into the right place. We wanted to fix this during the acquisition. So we've created a patent pending system within our scan generator and dimension software that uses a physics-based model of the scan coils. And then whatever scan pattern you want to use in your experiments, whether it's 2D STEM or 4D STEM, whatever that scan pattern is, we feed those scan coordinates into the model. We essentially predict the distortions, and then we modulate the output of the scan generator to compensate for those distortions. So instead of just telling the beam to go to the place that we want it to go to, we calculate where the beam actually ends up, and we created a correction in the scan controller so that the beam goes to the correct spot and we minimize distortions. And it turns out that this works really well. If you have the serpentine pattern that I showed you before, the uncorrected image is on the left. You simply click the enable distortion correction in our software, and you now can acquire data that looks like what's on the right, where you don't see these shifts, and you get a very nice image. This image on the right has no flyback time, so there's no delays on the right or left. There's absolutely no overhead. It's a fast dwell time of 2.6 microseconds in this case, so this should be very sensitive to the distortions. And there's been no post-processing added to this. This is simply what comes out of the data acquired by the scan controller and our software. You could also do something like the leapfrog scan, and if you do a leapfrog scan with a short dwell time, this distributed scan, you see artifacts as well. It's a different sort of artifact. But again, then if you turn on distortion correction, you see that the image cleans up quite nicely, and now you have interpretable images with minimal defects. So finally, STEM is unlimited. With our system, we have unlimited scan pattern options, unlimited subsampling, and these are enabled at high speeds due to our patent pending distortion correction system. So this really allows you to not only do 4D STEM experiments as you have in the past with a conventional raster scan. Certainly that's possible. You can do 4D STEM just like you always have. But now you're sort of future-proofed as well. So the development of new methods that use different scan patterns are all built into our system so that you can do a wide range of experiments, and it's really an impressive system. You might worry, though, that we have now added so many features. Does that mean that conventional imaging, if you're not doing 4D SIM experiments, for instance, is a software overly complicated and overly complex? So you may be used to software that looks something like this, where you have a large number of menus across the top, features hidden in all sorts of menus, a lot of icons of different toolbars at the top. It's all of the options are sort of available all the time, and it's really hard to find what you're looking for. It's really hard to train new users as well, because you have to teach them where specific functions are. It's not incredibly intuitive. And then you may have the situation where there's too many floating windows. I remember as a graduate student using the software to manually acquire data, and you would have every image pop up as a new window. And I sort of felt like it was the end of solitaire, where you have sort of this endless number of copies of things. And it was really hard to figure out what window was what when I was doing the experiments. So we have really tried to simplify the user interface with Mission Control. So we have several tabs across the top. The dashboard tab is the first place that you go. This is where you insert and retract the camera, cool it down, check system status. It's sort of a quick dashboard on overall system status, easy to access certain features. And we can hide or display different properties of the camera in the dashboard, depending on your particular installation. Then the next tab is for references. So for instance, collecting a gain reference, the first thing that you do is do a trial image. This gives you a histogram. You can see this on the left with this green bar. The image intensity moves across until it's in the green bar, and then you click stop and you click start the gain acquisition. It collects the gain reference and you're done. Collecting the references at the beginning of your day is straightforward and fast. There I've just collected a gain reference for one of our cameras, and that was at real-time speed. And then finally, you go to an imaging tab if you're not doing a 4D STEM experiment, and you can do things like see a movie of the image or an accumulated view. You can see a snapshot. You can display a side-by-side FFT, etc. The way the software is laid out is on the left side is really all of the controls that are relevant to the current experiment. So you'll see in the imaging tab here on the left side, there's nothing that has to do with scanning or 4D STEM or virtual detectors, because those things are not relevant to the imaging workflow. All that is shown is the properties of the camera and the experiment that are relevant to the current workflow. In this case, it's imaging, so all of the STEM features are not shown. On the right side then is the information about the currently selected display. So in this case, we've selected the FFT. You can see a histogram. You can select the contrast, the sort of display functions of the FFT. And you can draw things, make measurements. In this case, we measured the resolution of this ring from the gold on the grid. And so it's quite easy to deal with things. Things about the image always on the right, things about the experiment always on the left. Only what's relevant to the current workflow is shown, so you don't have to go hunting for a lot of features. You can see this is really straightforward and easy to use. And then, of course, we have the 4D STEM workflow that allows you to collect 4D STEM data extremely easy and straightforward. Again, I think that the training requirements for this software is quite low. This really makes this accessible to a wide range of your users so that they can focus on the science that they want to do and focus on the specimen. So finally, we've made 4D STEM easy, we've made STEM unlimited, and we've made electron microscopy intuitive with software that is really simple, easy to use, and accessible. So today I've introduced the mission control software, Dimension, and our scan generator, all of which are geared towards making your experiments easy, unlimited, and intuitive. The final thing I'll mention is that our software is built with an open API that allows it to be integrated with a number of software packages. We are integrated with the CEO's PantoRay software, as well as their hardware for EELS and FTIM, integrated with the Protochips Axon software, integrated with Serial EM for tomography and an automated single particle cryo-EM, for instance. And then the Open API also allows you to create your own custom control of our software. So all of the features of the software are available through the API, so that you can design your own automated 4D STEM experiments, for instance, using Python scripts and things like that. So this really makes this powerful for advanced users, in addition to be easy and intuitive and accessible for users who really just want to focus on their experiment. And with that, I'd like to thank you all for your time, and I think Bob will open it up for questions.
Yeah. Okay. Thank you, Ben. That was great. Thank you for giving us an overview of the new software from Direct Electron. So if you go up to the top bar, you should see a button that says Q&A. You might have to click on the three dots that says More to get to the Q&A window. So please go ahead and ask your questions if you have anything that you would like to know more about mission control, dimension, or any of the other Direct Electron products. I'll go ahead and ask a question that may be on some people's mind, which is for users that already have a camera from Direct Electron, maybe a DE64 or DE16, will they be able to upgrade their system to mission control and dimension?
Yes, that's a great question. So as you saw, some of the videos that were acquired at the beginning showing 4D STEM were acquired at UCLA with a DE64 camera, actually. So this software is applicable not only to our Celeritas camera, but also to our DE16 and 64 cameras as well. In some cases, there may be some upgrades to either the graphics card or the frame grabber card in the computer that are necessary. It sort of depends on your current configuration, but the software really is usable by those other cameras.
Okay. And you mentioned the DE FreeScan, the Direct Electron scan generator. Do you need the FreeScan in order to use mission control? Is it a requirement?
It's not a complete requirement to use the FreeScan with our software. However, many of the features of doing virtual imaging and things like that do require the FreeScan because we have to know where the beam is to calculate a virtual image. And so for the 4D STEM features, you really do need the FreeScan to take full advantage of the entire feature set. For controlling our cameras and all of the other features that we showed, especially towards the end, the FreeScan is not required.
Great. Okay. Would it be possible to get a demo of mission control? Is that something that wanted to see it somebody wanted to see it for themselves and see how it works? Is that possible to get it a demo?
Yeah, so the mission control software, we can certainly do a one-on-one meeting where we can walk through the software with you. Typically, we do that with a simulator, essentially, instead of a real camera, but that allows you to see the full features of the software. I'll also plug the fact that if you are at the microscopy and microanalysis meeting coming up in Cleveland, we will have a demo of the software in our booth, so come by and play with it.
Question came in about the metallic glass mapping. How is that, Barnaby? How was that data processed for the metallic glass mapping?
Yeah, so that data was processed by Carter Francis, who's a graduate student in Paul Voil's group at University of Wisconsin-Madison, which he did using Hyperspy and PixM and his own custom Python scripting. I guess the point to make there is our data is designed to be saved in easy to read open formats, HDF5 based formats. So that allows people to import the data into those open source 4D STEM programs and do their own analysis of the data.
Thanks. Ben, you showed a number of slides that had to do with the DE FreeScan scan generator, and I know you need a way to control the scan if you're doing 4D STEM. Does that mean that to use mission control that I have to have the DE FreeScan from Direct Electron?
Yeah, so you don't need the FreeScan to use mission control. We can assume that the scan pattern is just a raster scan pattern if you have a different scan generator. So you have the capability of doing virtual imaging, and there are labs using mission control already with their own scan generator, for instance, or a third-party scan generator. However, to use the features of unlimited subsampling options or unlimited scan patterns, things like that, having the FreeScan is really necessary. And I'll mention that the FreeScan and all of these options for subsampling and scan patterns, all of these things, are applicable to 4D STEM acquisitions as well as 2D STEM acquisitions. So when you choose your scan pattern or choose your subsampling or whatever the case may be, that is applied to acquisitions of 4D STEM data as well. And then the scan coordinates are saved with each frame so that it can be processed in your external software. So your external software, if you want to use Libertin or whatever, knows which frame corresponds to which location on the specimen.
Right. So we had another question about asking about the compatibility, that the FreeScan is indeed compatible with 4D STEM. So yes, that is the case. The FreeScan was designed for 4D STEM. Another question came in. The gain target value is related to the specific imaging condition. How to choose that? Does that?
Yeah, so the gain target value in the green region is essentially the region in which we can get a reliable gain reference. Our cameras are linear in response over that range, so the same gain reference should be applicable across that range. However, if you know a sort of target imaging condition, a target brightness, we always recommend that you acquire your gain reference at a similar brightness as what you're actually acquiring the data with, because that will sort of ensure that it is the best possible gain reference. But again, that sort of green region is relatively broad so that you can choose a value that's appropriate for your own experiments.
Okay. The question I had, the virtual masks, the ability to create the different virtual masks. What you showed in the slides were circles and donuts. So bright field, dark field masks. A lot of people use segmented STEM detectors for differential phase contrast imaging, things like that. Could you create the pattern? Could you create a virtual mask that is a segmented detector, that simulates a segmented detector?
Yeah, the shape of the virtual mask is really up to you. You could use wedges instead of full circles, for instance, things like that. You can calculate differences between different regions. It really is just up to the user in terms of how they decide to use their virtual detector. But we tried to build as much flexibility into it as possible, that what you would like to do is possible.
Okay. A couple of other things I'd like to bring up. Please ask some more questions. But in the meantime, I'd like to let people know, first of all, a big thank you for attending this webinar. We appreciate your time. We very much enjoyed the opportunity to tell you about our new software product, Mission Control and Dimension. If you want more information, you can visit our website. We've got product brochures there you can download. But also take a look at our YouTube channel. I'd like to really point out that we have tutorials posted on our YouTube channel on Mission Control, where we've done longer screen captures of Mission Control, showing the different features. You can see it actually being used in real-world conditions. Also, you can send us an email. You can contact us at sales@directelectron.com. But if you'd like to see a demo of Mission Control, please visit us at M&M in Cleveland, coming up in a couple of weeks. We'll be in booth 1210, which is right near the entrance. Come by. We'll have a kiosk with a computer running a simulator of Mission Control, and you can actually get a hands-on look and feel. Also, at M&M, we will be having a vendor tutorial on Tuesday at 5:45 p.m. And in that tutorial, we'll dive deeper into 4D STEM and how to use our products for 4D STEM. I think with that, we've completed the webinar. We've told you about our new 4D STEM software, Mission Control with Dimension. And we want to thank everybody for attending. Appreciate the time you spent with us today. And certainly follow up if you have any more questions. I hope to see you in Cleveland. Bye-bye.